So these little guys are pangolins. This is a baby riding his mother's back. They are the world's most heavily trafficked mammals. Their scales are erroneously believed to have healing properties in traditional Eastern Asian medicine. They live in Africa and in Asia. They are the world's only scaled mammals, and they are adorable and utterly vulnerable. Uh, Thought I'd raise awareness to a worthy cause. They're being hunted in the wild, and it's quite sad. They're wonderful, adorable critters. If you haven't heard of them, Google them. That's spelled pangolin, pangolin. It's from, I believe, a Malay word meaning for something to roll. That's something that rolls up into a ball. Well, that's our intermission for now. Let's get back to the show. And hello. This should be the final part of this episode. I just should mention the first thing before we continue. I should mention that this theorem from part 2, where I talked about the properties of unfamiliar fields, and that when a field is unfamiliar to a prime, then that the Galois group of the l-adic completion is the same thing as the Galois group of the underlying field itself. I consulted with the mathematicians who know more about this stuff than I do, and I needed to add that this only works if K is a Galois extension of Q. It doesn't work if K is not a Galois extension. Fortunately, all the extensions will be working with our Galois, so yeah. Okay. So we did all of our exercises, and also I apologize. I got the Legendre symbol wrong. It's 1 if it is a perfect square, and -1 if it isn't. I'll amend the previous episode with an errata to cover this. Anyhow, so far what we've discussed is the need to explore the p-adic absolute values of algebraic numbers, and then we've studied valuations, absolute values, places, and embeddings, and how all of those things summarize the different ways we can deal with the problem of computing the p-adic absolute value of a given algebraic number. There's 2 big applications of this stuff. One is a number theoretic application of its own right, and the other is, of course, to our Collatz stuff, but we're going to deal with the former first, which is the product formula. So, as I said, there are 2 reasons why paying such a great tribute to algebra Moloch in this episode is necessary. As we said, the first is the very practical matter of computing expressions like this, but the second is the famous product formula, which is really just an absolute value theoretic generalization of the fundamental theorem of arithmetic that every positive integer greater than or equal to 2 can be uniquely written as a product of primes up to a plus or minus 1 and a rearrangement of the primes in the product. Actually, no plus or minus 1 because it's positive. Okay, so consider the rational number 22/7, a well-known approximation to pi. Because its numerator and denominators are elements of z, we can uniquely factor them as 2 times 11/7. So, letting p be any prime, we have that the p-adic absolute value of 22/7, well, this will be 1/2 if p is 2, 7 if p is 7, and 1/11 if p is equal to 11. And for all other primes p, it's equal to 1. That's because for all of these various primes, they're co-primed, the numerator and denominator. Taking the product over all primes p, we then get that the product of the p-adic absolute value of 22/7 is 1/2 times 7 times 1/11, which is 7/22. And so 22/7 times the product of its p-adic absolute values over all primes p is equal to 1. And this is the product formula. Let R be a non-zero rational number, then the real absolute value of R times the product of all the p-adic absolute values of R will always be equal to 1. The reason why this infinite product converges is due to the fact that any rational number will contain only finitely many prime factors in its numerator and denominator. And so for all but finitely many primes p, this product is equal to 1. And therefore it reduces to a finite product and converges. But how it reduces, of course, depends on our choice of our rational number r. And the proof, of course, is just fundamental theorem of arithmetic. So we can do so many things with this. And just so as an example, this is just something that I discovered while doing the research for my dissertation, and it's just fun. I'm basing this off of Matt Baker's fascinating blog post about a p-adic proof that pi is a transcendental number. And so this involves using the product formula. So we begin in 1894 when Émile Borel made the following clever observation about power series over the complex numbers. Let f of z just be a power series with complex variable z, in complex variable z, where the an's are integer coefficients, and let's suppose it has a radius of convergence big R. If big R is greater than 1, then f of z is necessarily a polynomial. And the proof is by the Cauchy estimates on the an's. If big R is greater than 1, then there's some little r strictly between 1 and big R, so that f of z is holomorphic on the closed disk centered at 0 of radius r. So applying the Cauchy estimates, we know that the complex absolute value of the an's is going to be equal to the absolute value of the contour integral, which is then, of course, less than 1 over 2 pi times the supremum of f of z's absolute value over this contour. And here, because z is on this contour, z is going to have absolute value r, and so we get this. Since r is bigger than 1, and n is arbitrary, we can let n go to infinity. This quantity will decay to 0 as n goes to infinity. However, there is in particular, there will be a sufficiently large value of n for which this thing is less than 1. But since the an's are integers, if an integer is less than 1, in absolute value, it has to be 0. And so that forces the an's to be 0 for all sufficiently large n, and that proves it. Borel extended this result to the case where the power series defines a meromorphic function with integer coefficients. Provided that the series radius of convergence is greater than 1, is strictly greater than 1, the series must sum to a rational function. In other words, if we can extend the radius of convergence of our power, if our power series has a radius of convergence bigger than 1 and has integer coefficients, then it must represent a rational function. Others, such as Polya, have further generalized it, though for our purposes, the most relevant generalization is the one due to Bernard Dwork. So this is Dwork's theorem. Let f of z be a power series of a complex variable z, where the coefficients an are elements of q. Let S be a collection of finitely many places of Q, including the infinite place. That is, let S be a collection of primes. For every prime not in S, the an's have p-adic absolute value less than or equal to 1. In other words, for all but finitely many primes, the an's are p-adic integers. For every prime in S, there is a disk dp in the p-adic complex numbers centered at 0 of radius rp, so that f extends to be meromorphic on dp. And moreover, if we take the product over all the primes in S of that radius, we then get that total product is greater than 1. In particular, this means that this disk, it contains 0, and for any two elements in the disk, their p-adic absolute value, the p-adic absolute value of their difference is at most rp. And so it's just worth pointing out for later, this can be thought of as an early instance of my frame theoretic approach. And the idea is this, because f of z has rational coefficients, we can embed those coefficients in any metric completion of Q, and by studying them from all of those different perspectives, we then get a result. And so this is an example of frame theory in action. Rather than considering this object solely as a complex valued function, rather we can think of this as a formal power series with coefficients in Q, and therefore we can embed it in the spaces of formal power series with coefficients in QP for every prime P, and thus by making conclusions about those embeddings, we can draw conclusions about the underlying object. So now, so here's the proof of this result. For simplicity's sake, I'm going to follow Matt Baker, and we're going to prove the simpler case that f is a polynomial whenever it is analytic, that is holomorphic, on the dp's rather than meromorphic. So we're going to say that here we're going to change meromorphic to a polynomial, and in this case, and all that matters in this is that the underlying. Do I have to say any other details? Yes. So here the difference is that when f is meromorphic on the disk, then f is a rational function. What we're going to prove is that when f is analytic on the disk, then f is a polynomial. And the key idea is that the Cauchy estimates work in a p-adic context. That is, the Cauchy estimates are a frame theoretic phenomenon, and that they transcend the particularities of whatever valued field we happen to be examining our analytic function on. All that matters is that the underlying valued field be complete and algebraically closed. So let's just where is it by 2? Yes. So this is as we said, this is a function with rational coefficients. So this, again, treating this as a formal power series, let's replace this complex variable z with a p-adic variable z. Then this is an analytic function in the p-adic world, and in particular, the products of all of these radii is going to be greater than 1. So when you this is just important, when you have an analytic function defined by a power series in a valued field, if we then necessarily have the condition that we have this Cauchy type estimate, that in particular this decay must go to 0. Basically, what this is that if you have a formal power series with rational coefficients, and if there is a p-adic number, which when you evaluate the series at it, your result is convergent, then the p-adic absolute value of an times the p-adic absolute value of the integer you picked to the power of n, or the number you picked to the power of n, that has to tend to 0 as n goes to infinity. So in the fact when you're working over the reals instead of the p-adics, technically big RP here has to be any real number strictly less than RP. However, when you are in the non-Archimedean world, it's a fact that a power series, either in a non-Archimedean space, it either converges at every point on the boundary of its disk of convergence, or it fails to converge at every point. And in particular, if it converges on the boundary of its disk, then we have this occurs. So with this limit condition, and this is just the Cauchy estimate phenomenon, is given a power series with rational coefficients an, if big RP is the radius of convergence of that power series as a function over the p-adics, then the ans must decay p-adically in a manner proportional to 1 over rp to the power of n as n goes to infinity, and this is going to occur for all primes p in our set S. Yeah. So note that because S contains the infinite prime, we also have that this estimate occurs for the ordinary absolute values of S. Moreover, since S is finite, we can multiply all the big RPs together and without things blowing up. And in particular, this proportionality then leads to this proportionality where we've now gathered together all the information from all the different primes, and this is less than some 1 over big R to the n for some real number big R. This then goes to 0 in the reals as n goes to infinity. On the other hand, by 1, we had that if p is not in our set of primes S, this is going to be a p-adic integer. And so, in particular, this is true for all of the primes p. So we have the product over all of these primes has to be less than or equal to 1. Now we appeal to the product formula. And this is for any given n. And note that for any given n, there's going to be only finitely many primes p for which this absolute value is not equal to 1. So this product is convergent. Now we appeal to the product formula. 1 is equal to the real absolute value of an times the product of the an's p-adic absolute values over all primes p. This is then the product of all the primes in S over all the primes not in S. This is then less than or is bounded by 1 over r dn, and this is then bounded by 1, and so as n goes to infinity, this decays. But this then tells us that, again, we get this contradiction where our upper bound is smaller than 1, which gives us the desired contradiction. In particular, this applies only if just remember, the only reason the product formula doesn't work is if the thing we're applying it to is 0. So the fact that this is going to lead to a contradiction if n is sufficiently large means that an has to be 0 for all sufficiently large n, and so therefore f is a polynomial, and that proves the result. Famously, Dwork would use this theorem as his central tool for proving the first of the 3 while conjectures, which is that the zeta function of a finite field is a rational function. This was later proved using fancier techniques, but the p-adic analytic proof was the first one, and this was actually the first of the while conjectures to be resolved. Excuse me. So this example shows the fundamental analytic utility of a product formula for a number field. It's essentially a kind of arithmetic uncertainty principle, in analogy to the famous uncertainty principles of quantum mechanics and harmonic analysis. Equation, where is it? 9.09. Yeah. Yes. So what this thing tells us is that if r, say, is a very, very large real number, then there must be primes for which r's p-adic absolute value is very small. Conversely, if there are primes p for which r has a very, very large p-adic absolute value, then r's real absolute value has to be quite small. So there's this duality between the two, and we can never make all of them simultaneously small unless the r we're looking at is 0. So what makes this useful is the fact that the product formula is one of the few places in mathematics where p-adics interact with q-adics. And so, guys, one of the big problems, especially in arithmetic geometry and algebraic geometry, is that p-adic spaces and q-adic spaces for distinct primes p and q really have nothing to say with one another. As we were seeing when we were doing p-q-adic analysis, there's no such thing as polynomials or power series or analytic functions in a p-q analytic context, precisely because there's no way to naturally multiply a p-adic number by a q-adic number. However, there's a caveat here. Both the p-adics and the q-adics contain the rationals as a subfield. So the one case where we can multiply a p-adic number by a q-adic number is if they're both contained in the rationals. More generally, even though the p-adics and the q-adics are going to be very distinct as valued fields, there are nonetheless going to be elements that they share in common. For example, if you have any 2 primes which are congruent to 1 modulo 4, then both of those primes, the associated p-adics will contain an element which is an embedding of I, a primitive fourth root of unity. So in this respect, we can make the p-adics and the q-adics work together by instead, rather than looking at what they don't have in common, we look at what they do have in common. And the product formula is one case where this really does occur. For any given, in this case, R is being realized as a p-adic rational number for all primes p. And this product makes sense because it's being witnessed by the global field Q. And so the product formula in my work I conjecture its use comes from the fact that it will allow us to pass from p-adic information to q-adic information. Ideally, in the basic setup, and I'll just mention this more a little bit later, is that if you have a rational number whose behavior you want to study, it might turn out that its p-adic behavior is easier to control than its q-adic behavior. So we then, in analysis, we use the good control we can get on p-adic to try and counteract the lack of good behavior on the q-adics. Now, this is very specific to what we're doing here, where our functions take values in global fields, because the moment we consider real or complex analysis, as traditionally done, this isn't possible anymore, because because a randomly selected complex number or real number is going to be a transcendental number, and there's no way to make sense of transcendental numbers, and there's no natural way to make sense of them as elements of the p-adics. But in our case, when our functions and their Fourier transforms lie in given number fields, we can use the product formula to take advantage of this fun coincidence. So the remainder of this subsection is going to be dedicated to stating the product formula for an arbitrary number field k. And as one would expect from algebra, to do so, we need to introduce some more terminology. So the problem is that while the classic product formula for Q is very simple, when we consider a number field K, we're going to have to weight these various absolute values with exponents. And so this leads to the notion of a normalized absolute value. So let K be a number field of degree D, and let Z be a non-zero element of K. Given a place V in Vk, I'm going to write this to denote the following. It's going to be 1 if V is the trivial place. It's going to be the complex absolute value of the image of Z under the embedding iota in the case that V is an Archimedean place associated to a real embedding. It's going to be the square of iota of Z's complex absolute value if V is an Archimedean place associated to a complex embedding. And it's just going to be our p-adic absolute value when V is a non-Archimedean place. And so here, recall, this is going to be the ideal norm of P to the power of negative valuation P of Z. We then extend double bars V to K by defining 0 double bar V to be 0 for all valuations. This is sometimes, Milne calls this a normalized absolute value, although he mentions, somewhat tongue-in-cheek, that when we're considering a complex place, this is no longer an absolute value. He just says the best way to deal with this is to just ignore it. Some people call this a normalized almost absolute value, which is a mouthful, so that I will call this a normalute value. I like the way it sounds. It sounds like Malamute, which is a very large type of dog that you find in the Pacific Northwest. So, again, we're going to continue our abuse of notation by writing, with this subscript, we will allow it to be a prime, a valuation, or an embedding. And we also allow the prime to potentially be the infinite prime if we like it. So in this terminology, with our normalute values, our product formula is as follows. Let K be a number field, and let Z be a non-zero element of K. Then the product of the v-adic normalute value over all places of K is going to be equal to 1. The proof of the product formula is based on the following lemma, which is in some sense even more fundamental than the product formula itself, because the lemma, it ties together all the concepts we've covered so far: valuations, primes, norms, and normalute values. And by norms, I mean field norms. Let K be a number field, and let V be a finite extension of K. Then, for any Z in K and any non-trivial place V, if we take the product of the w-adic normalute value of Z over all places W of VL, which lie over V, then that is going to be equal to the v-adic normalute absolute value of the field norm of L over K. So what this says, and we're getting to this into a bit of in a moment, is that this is where the dichotomy comes into play. Remember, there's the global approach and the local approach. The local approach is where we use the field norm to then get the absolute value, whereas the global approach is we use the various primes that lie above whatever prime we're studying. And so this says that the reason why the primes proliferate is because, not the reason why, but when the primes proliferate as we go from K to L, that's going to cause us to have to take into account the increasing degree of L over K via the norm. And with this lemma, the proof of the product formula is wonderful, and it's simply a matter of we're going to reduce the product formula for K to the product formula for Q by using the field norm of K over Q to go from Z in K to a rational number in Q. So here's the product formula over all the normal absolute values. Here's our trivial absolute value, here's our Archimedean absolute values, and here's our non-trivial, non-Archimedean absolute values. Since Z is non-zero, this is 1. This is then going to be the p-adic absolute value for all prime ideals P of OK. This, of course, we just leave it alone by the lemma here, because then another thing is this works for both the Archimedean and non-Archimedean places. So when we multiply over the v-adic normal value of Z for all Archimedean places of K, that's then going to be equal to, by the lemma, the field norm of Z over Q, and then it's going to be its ordinary real absolute value. Here, we can then, since every prime ideal of OK lies over some prime number P, we can group these according to all the prime ideals that divide P for every prime P. Then, by our lemma, the product of, in this case, for all prime ideals P that divide P, it's going to be the p-adic absolute value of the field norm. And then here, this is the product formula for Q, because this is a rational number. And then we get 1. So now, just to give an even clearer statement of the lemma, as introduced in notation, ELK, remember, is the set of all embeddings of K into QL bar. We saw that those embeddings will be equivalent to one another if and only if you can get one from another by post-composing by a field automorphism that leaves QL fixed. So I'm going to write EL of K twiddle to be the set of equivalence classes of the L-adic embedding space under the conjugacy relation. And in particular, each of the individual, there's a one-to-one correspondence between the elements of this space and what I call the structure classes of this set. And so then this gives us our really nice summary that brings everything together. So let K be a number field, let Z be a non-zero element of K, and let L be a possibly infinite prime of Z, and let P be a prime ideal of K lying over L. Note, if L is the infinite prime of Z, then P is going to be an infinite prime of K. Then we have the following equalities. The product of the p-adic absolute value of Z over all primes of L is, in this case, do we need the infinite? This should be the norm rather than this should be the norm here. I believe the normal value. But anyhow, we get that it's equal to the product of the L. So this is the global approach here. And then we have the local approach here. We get this by taking the product of the L-adic absolute value of the image of Z under an embedding iota, and we pick one embedding iota for each structure class of EL of K. And then this is going to be the same thing as the L-adic absolute value of the field norm of Z. And so if we look at just the finite primes, we have the following. The product of the v-adic normalute value of Z over all the finite places of K is going to be equal to the product of over all prime numbers L of the L-adic absolute value of iota of Z, where iota is an embedding in one of the structure classes correspond of L-adic embeddings of K, and we have one iota for each embedding, and so we get this. So as an example, just as what we saw earlier, from our factorization of 5 in this ring, and here's p1, p2, p3, we had that these absolute values were as follows. When we multiply them all, we get 1 over 5 to the 6th. And note that since this field has degree 6 over q, the norm of 5 is equal to 5 to the 6th. And so the product of the p-adic absolute value of 5 for all primes p of this field that divide 5 is equal to 1 over 5 to the 6th, which is equal to the 5-adic absolute value of the field norm of 5, exactly as the lemma told us would happen. So now, as I said, I had an idea for using this stuff. Here's one of them. So the thing is as follows. Suppose we want to study chi q of z minus x for some integer x. Here, let fn of z denote the convolution of chi q with the nth q-adic Dirichlet kernel, and then we subtract x. This is the nth partial sum of the Fourier series generated by chi q hat, and that's going to be a rational valued function that's locally constant modulo 2 to the n. And so, since this is a locally constant rational function, we can, taking values in q, the product formula gives that the 1 over the real absolute value of fn of z is going to be equal to the product over all prime numbers p of the p-adic absolute value of fn of z. Now, since fn is locally constant modulo 2 to the n, its image is going to contain at most 2 to the n distinct rational numbers. And so this is a finite set of rational numbers. And so let's let S of Sn be the set of all prime numbers that occur as divisors of either the numerator or the denominator of some element of this set. Since we have finitely many rational numbers, we can only have finitely many prime factors of their numerators and denominators, so Sn contains finitely many primes. By construction, if a prime p is not in Sn, then it's in neither the numerator or the denominator of any fn of z, and so we then get that this must hold true for all z in z2 whenever p is not in Sn. So our product formula will then reduce to the finite product of all primes in Sn. Now, since fn is locally constant modulo 2 to the n, it has a Fourier transform, fn hat, like this. And so here's what we can do. To study this reciprocal, all we need to do is examine this thing, and in particular, so unfortunately, working with estimates in p-adic world is not as easy as it is in the real or complex world because we don't have the Archimedean stuff. And they said the p-adic ultrametric inequality makes things kind of goofy. However, we can use this to our advantage. What it basically says, remember, is that the p-adic ultrametric inequality says that the p-adic absolute value of a sum of terms will be equal to the p-adic absolute value of the largest of the terms, assuming one of the terms has a larger p-adic absolute value than any of the other terms. So what this tells us then is we want to study this thing. We can use the Fourier coefficients, the Fourier transform, by trying to group the terms of this sum in a particular way. For example, we can do the level set sum, where we write this as fn hat of 0 plus the sum from n equals 1 to big N of the sum over all t's with 2-adic absolute value exactly to the little n. And so when we do that, that's the method we use to sum the Fourier series in episode 1, we can then get some estimates there, and possibly by choosing a different arrangement of terms, we can arrange that cancellations occur, and then use that to obtain estimates. The really useful thing, really important thing is because of the equality condition in the ultrametric inequality, we can use this a method to get lower bounds. Because what we do is we just group the terms in such a way that one of them is strictly larger than all of the others. Then instead of an inequality, we get a direct equality, and we can then estimate the absolute value of the thing we got directly for using upper or lower bounds and number theory. Note that we can also do the following setup, where instead of considering the real absolute value, we consider the q-adic absolute value. And here we can directly apply the correspondence principle. The correspondence principle tells us that if there is a z0 in z2 prime, which is the set of all two-adic integers which are not non-negative integers, if there is such a z0 such that this q-adic absolute value tends to 0 in R as n goes to infinity, then x is either a periodic point or divergent point of TQ based on whether z0 is rational or irrational, respectively. So in particular, if, for example, z0 is a rational number such that this quantity goes to 0, then this thing is going to have to go to infinity because the denominator it shrinks. So we then have the following theorem. X is a periodic point of TQ, the shortened QX plus 1 map, in Z take away 0, if and only if there is a rational two-adic integer Z with infinitely many digits, so that the limit of the real absolute value of Fn of Z times the product of the p-adic absolute values of Fn of Z for all primes P not equal to Q tends to positive infinity. And in fact, we can show more. From the correspondence principle, it follows that if the F series of chi-q is evaluated at a rational two-adic integer and converges to a positive integer, then that convergence will occur not just in the q-adic topology, but also in the topology of the reals. That is to say, there are points in the F series, there are points in the two-adic integers where if you plug that into the F series, you can get the correct sum for the F series, regardless of whether you use the q-adic topology or the real topology. And so in particular, we then have that X is a periodic point in TQ, of TQ in the non-negative, in the positive integers, if and only if there's a rational two-adic integer Z with infinitely many digits, so that the real absolute value of Fn of Z tends to 0 as n goes to infinity, which then by the product formula occurs if and only if for each n and the product of the p-adic absolute value of Fn tends to infinity. So in this case, to show that X is not a periodic point, it suffices to get an upper bound on the periodic point in n1. It suffices to get an upper bound on the p-adic absolute values of Fn for all p. I'll have more to say about this stuff in episode 8 when we finally get into all of the nitty-gritty details. So now again, we started this with a concrete problem in mind. And so let L be a prime of Z, while in general, as we have seen, the problem of making sense of and subsequently computing the L-adic absolute value of an algebraic number alpha is going to be a rather involved process. We are fortunate that the alphas that will occur most often in our work will come in particularly tractable form. In particular, we're going to have them in the form P of Xi, where P is a polynomial with rational coefficients, and Xi is a root of unity. So we already saw this in the functions here, which occur in the product defining a q hat of t. This takes values in the cyclotomic field e to the 2 pi I over the two-adic absolute value of t. Another example comes from an expression of the form 2 to the m minus q to the n. This occurs in the denominator of chi-q of b2 of n. For b2 of k. And so for integers here, m and n are greater than or equal to 2, we can factor this as either this product or this product. And so here it's either going to be nth roots of 2 and primitive nth roots of unity, or it's going to be mth roots of q and mth roots of unity, which take values in this field and that field. As a result, there are enough concrete cases like this that the patterns are worth noting in their own right. Here, though, this is it's important to notice that these, in this case, these fields are going to be Galois extensions because we have both 2 to the 1 over n and e to the 2 pi I over n. But if we didn't have the root of unity, it wouldn't be a Galois extension. So again, in general, our work is going to be with Galois extensions, so everything is nice. So now we need to go over cyclotomy. So let n be a positive integer. Then the nth cyclotomic polynomial, big phi n of x, is the integer coefficient polynomial given by the product of all of the primitive nth roots of unity. And so remember, this is my notation for the set of positive integers in 1 through n, which are co-prime to n. And so the various properties of cyclotomic polynomials, just to recall, let p be a prime and let q be an odd prime. The degree of the nth cyclotomic polynomial is the Euler-Toscan function of n, which is the number of positive integers less than or equal to n, which are co-prime to n. Then we just have the following useful properties. If we take the product of the dth cyclotomic polynomial over all divisors d of n, we get x to the n minus 1. For a prime p, phi p of x is just the sum, is that series. Phi p to the n of x is this thing. And for n, and this is a factoring rule, phi n of x is going to be equal to phi p up of n, x to the p vp of n minus 1, where vp is the p-adic valuation, and up of n is the projection where we take n and we multiply it by its p-adic absolute value. So this is a projection from qp onto the group of units of zp cross. If n is not a prime power, then phi n of 1 is equal to 1, and phi n will be irreducible over fp and qp if and only if the powers of p generate z mod nz cross, and the minimal polynomial of e to the 2 pi I over n over either qp or fp is equal to the nth cyclotomic polynomial if and only if p is not congruent to 1 mod n. And so with this, we get a collection of formulas for dealing with the l-adic absolute values of expressions involving roots of unity. We begin at the highest level with trigonometric polynomials. Let L be a prime number, let n be an integer greater than or equal to 1, and consider a polynomial p with l-adic coefficients. If Cn is unfamiliar to L, that is, if Q of Cn contains no subfields other than Q, which can be embedded in QL, then we have that the l-adic absolute value, there should be a k here, is the l-adic absolute value of p of Cn is equal to the product of p of Cn to the k when k is taken over all integers 1 to n that are co-prime to n, and then we take the l-adic absolute value, and then we take the phi of nth root. So let everything be as given. Since Cn is unfamiliar to L, the Galois group of QL of Cn over QL is then equal to the Galois group of Q of Cn over Q, and so we have this. It's known that this Galois group of the nth cyclotomic field has cardinality phi of n, and that the Galois group is isomorphic to Z mod nz cross. Specifically, every element of the Galois group acts on Cn by a map of the form Cn gets mapped to Cn k sigma for some unique k sigma in Z mod nz cross. So next, let's deal with terms of the form a minus b c for a root of unity c. Let k be a number field, and let c be any primitive nth root of unity, and let L be a prime number not congruent to 1 mod n. Then for any a, b in QL, with b being non-zero, the l-adic absolute value of a minus b c is equal to the l-adic absolute value of b times the l-adic absolute value of phi n of a over b. Then we take the phi of nth root, little phi of nth root. And so the proof, let everything be as given. Since L is not congruent to 1 mod n, this Galois extension is unfamiliar to L because all the none of the power will be dividers. So we then get that the field norm of A over B minus C, where we take here the field norm we're in the l-adic world, because of the unfamiliarity, we can pass from the Galois group of C over QL, and this means the smallest Galois extension of QL containing C. This is then going to be equal to the product over all the smallest Galois extension of Q containing C, which of course is just Q of C, since C is a primitive root of unity. And then, because A over B in this case, I should move this out. Because the A or B are in QL, we can move sigma in, and just because it ignores this. And then since by definition phi of n of x is equal to the product of x minus sigma of c when sigma is in this Galois group, we then have that the product here is just equal to big phi of n over a evaluated at a over b. Since L is unfamiliar to C, every automorphism here induces an automorphism on QL of C, which leaves QL fixed, and as a result, this automorphism is an isometry with respect to the L-adic absolute value, and so we get that the L-adic absolute value goes inside, and it's then going to be constant, and so it's this to the power of the cardinality, and the cardinality is phi n. For a more general case, it's helpful to use the following terminology, that I will say an algebraic number is Galois whenever Q of alpha is a Galois extension of Q. So let Z be a Galois algebraic number, and let L be a prime unfamiliar to Z. Again, that means that the Q of Z does not contain any subfield other than Q, which is embeddable into QL. Letting P be the minimal polynomial of Z over Q, then for all A and B in QL with B non-zero, we have that A minus BZ's L-adic absolute value will be equal to the L-adic absolute value of B times in this case, this is going to be the degree of the Galois closure of Q of Z over Q, which is just equal to the degree of Z over Q as an algebraic number, and it's going to be the L-adic absolute value of the minimal polynomial of Z evaluated at A over B. And the proof is basically identical to this one right here. We just replace C with Z, big phi n with P, and little phi n with the degree of Z over Q. We can also deal with congruences. And the idea is, it's pretty straightforward. So let C be a primitive nth root of unity, and let L be a prime number not congruent to 1 mod n, and let P of x be some polynomial with coefficients in QL. Then we can, by just using cyclotomic polynomials to simplify everything, we can then rewrite P of C. Well, it's going to be a sum of AK, CK, where the AKs are unique scalars in QL, and we're going to be summing over K. Well, K is going to be 0, that's the constant term, and then it's going to be taking every value in Z mod NZ cross except for n minus 1, because the nth minus 1 value is related to all of the others via the cyclotomic polynomial relation. So writing it like this, we then have that for an integer m greater than or equal to 1, P of C will be congruent to 0 mod L to the m if and only if the coefficients here are all congruent to 0 mod L to the m. So in other words, when you have a root of unity which is so that it's unfamiliar to QL, then to figure out the value of a polynomial mod a power of L, you just look at the coefficients of the polynomial. So as an example, let Q be any prime number, and consider the polynomial P of x equals 3x to the fourth minus 4x plus 1, and we're going to be considering C5 equals e to the 2 pi over 5. There are two cases here based on the friendliness this is from the older version, based on the familiarity of 5 to Q. Suppose 5 is familiar to Q. This happens when 5 is a divisor of Q minus 1. So for example, let's consider Q equals 11. There are noting that 2 is a primitive root of unity mod 11, we find that the powers of 2 mod 11 are as follows. And so 4, 5, 9, 3, and 1 are the five fifth roots of unity mod 11, and of these only 1 is non-primitive, so that makes 3 the smallest primitive fifth root of unity. So by our convention then, we define e to the 2 pi over 5. It's going to be the unique fifth root of unity in Z11, whose first 11-adic digit is 3, and as a result, p of e to the 2 pi over 5, that's this, mod 11, this is going to be 3 times 3 to the fourth minus 4 times 3 plus 1, which is equal to 232 congruent to 1 mod 11. Since the value of p, if this is mod 11 is co-prime to 11, this then tells us that this quantity here has an L-adic 13 has an 11 adic, absolute value of 1. So let's do a Hensel lift. To compute the value of the polynomial mod 11 squared, just see what we would need to do, we would need to then find the unique primitive fifth root of unity in z mod 121z, which is congruent to 3 mod 11, etc. So, on the other hand, suppose q is unfamiliar to 5. Then q is not equal to 1 mod 5, and so this is going to be a vector space of dimension 4 over the q-adic rationals, and its basis will be this set. So we're then going to use the cyclotomic relation for the fifth roots of unity to then reduce p of c5, and we do this reduction, and we get that it is going to be -2 minus 7c to the fifth minus 3c 5 squared minus 3c5 cubed. So given any element of qq of c5, if we write this equality here, and just use respect to this basis, its coordinates are a, b, c, d, then the congruence, z is congruent to p of c5 modulo q to the n. Well, that's going to occur if and only if a is congruent to -2 mod q to the n, b is congruent to -7, c is congruent to -3, and d is congruent to -3. For the absolute value, since we have an unfamiliar case, the q-adic absolute value is just going to be the q-adic absolute value of the field norm, and then we take the root of it over the degree. So here the degree is phi of 5, which is 4, and then here we're going to take the product over all of the primitive fifth roots of unity, and so this is, in that case, this is going to be k goes from 1 to 4 of here, and so we just write out the product, sum it, we use our cyclotomic identity to reduce it, and we get that this is the q-adic absolute value of this thing for an unfamiliar prime q. It's the fourth root of the q-adic absolute value of 2 squared times 181, where both the 2 and 181 are prime numbers. So remember, this unfamiliar case is going to occur only when 5 is not congruent to 1 mod 5. So if q is any prime not congruent to 1 mod 5, well, here the only primes for which this can be not equal to 1 are 2 and 181. But 181 is congruent to 1 mod 5, so it doesn't count. It's a familiar case. So all we're left with is the q equals 2 case, in which case we have that for any prime number not congruent to 1 mod 5, the q-adic absolute value of this expression will be 1 if q is not equal to 2, and the fourth root of 1/4 if q is equal to 2. Finally, we have our applications to chi-q. So with all the details now accounted for, we can continue on in the vein of what we were discussing at the start of the episode. And since fleshing out the ideas in the motivational section at the beginning of this episode is a research project in its own right, rather than continuing with those ideas directly, it helps to simplify things by considering one very specific idea that's really trippy, and it gets us into frame theoretic stuff that we'll be talking about in the next episode. And this involves studying chi-q hat. What we're going to do is we're going to define a form of the field norm that works for functions taking values in q bar. So, and it's the form that we said. Recall that given an algebraic number f of hat of t, n of f hat of t is the field norm of f hat of t in the field q of f hat of t. In other words, it's the field norm of f hat of t over the smallest number field containing f hat of t, and then the operator n of f. Well, this n of f hat, then at every value t, it takes the value equal to the norm of f hat of t over the smallest field containing f hat of t. In the case, remember that I write that this is the Galois closure of this field. We can then use Galois theory to say that big N of f hat of t is the product of the elements of the Galois group of f hat of t over q, and that. And in particular, by the properties of field norms, this is going to be an integer precisely when f hat of t is an algebraic integer. Now we're going to proceed, going to compute n, the norm of aq hat, and we'll do this in several steps. First, we need a functional equation. Let t be non-zero, then 1 plus q e to the negative 2 pi I t over 4 times aq hat of 2t is equal to aq hat of t. Well, suppose t is non-zero, and then we just plug into the definition. 2t here. This is v2 of 2t is going to be 1 plus v2 of t, and since that negative, we get a minus, and so this reduces, and we just pass from 2 to increasing n by 1. We then decrease n here by 1 to increase n in the lower and upper limits by 1, and this, of course, this should be a minus. There should be a minus 1 here, and then so all we have here is we're missing the n equals 0 term, and that gives us that, and we multiply on both sides to get the identity. Now what we're going to do is we're going to compute the field norm of this function, and it's going to be equal to, for a non-zero t, it's 1 plus negative q to the power of the q-adic absolute value of t over 2 divided by 4 to the power of the q-adic absolute value of t over 2. When, just to check this, when t equals 1/2, this is going to be the rational number 1 minus q, and so its field norm is just itself. On the other hand, when t equals 1/2, this formula here, the q-adic absolute value of 1/2 is 2, so we get 2 over 2 and 2 over 2, which are 1, and so we get 1 minus q over 4, so the formula works when t is 1/2. So let's let t be a element of z2 hat whose q-adic absolute value is greater than or equal to 4. Let r of t be this algebraic number, and let p of x be the monic minimal polynomial of r of t over q. Since e to the negative 2 pi I t is a primitive t-tooth root of unity, because that's the denominator of t, r of t is going to take values in kt, which is this cyclotomic field. Since cyclotomic fields are Galois, we then have that the norm of this is going to be equal to the product of the Galois conjugates. And since this is a Galois automorphism over q, it ignores this stuff and only concerns this. By algebraic number theory, we know that this Galois group is isomorphic to the multiplicative group z mod t2 z cross. And in particular, for every sigma in this group is going to be of the form of the q linear field automorphism, which sends e to the 2 pi I t to e to the 2 pi I m sigma t for some unique integer m sigma in z mod t2 z cross. Consequently, here's the product over the Galois conjugates. We then rewrite this using the isomorphism. I'm then going to factor out a negative q over 4, so that this is then going to be negative 1 over q minus e to the negative 2 pi I mt. Pull this out, and then we get to multiply this, raise this to the power of the cardinality of this set, which is the t2 over 2. Here, note that the set e to the negative 2 pi I mt, as m varies in z mod t2 z cross, this is going to be the same thing as the set of primitive t-tooth roots of unity. So this product is then by definition the t-tooth cyclotomic polynomial, which is x to the t-tooth t2 over 2 plus 1. So this thing then is what we get when x is equal to negative 1 over q. So our product here is the cyclotomic polynomial at negative 1 over q, which is this, and then we multiply through and simplify, and we get the desired result. Now here's the main computation. Let t be non-zero. Then the norm of aq hat of t is equal to this quantity times the square of the norm of aq hat of 2t. And consequently, by an inductive argument, we get the following messy expression as the field norm of aq hat of t. And this product is, by our usual convention, is going to be 1 when t is 1/2. So letting t be non-zero, here we're going to use the properties of field norms. So by definition, letting kt again denote the cyclotomic field, this is the smallest number field containing aq hat of t. So by definition, this thing is the norm of kt over q of this number. We then use our functional equation, and then we then use the multiplicativity of our norm. Now we're going to use the interaction between field norms and towers of extensions. We know that whenever we have a finite extension tower, fkl, the norm of L over F is going to be equal to the norm of K over f applied to the norm of L over K. Here, our extension is k2t kt. So, for example, if t is 1/8, this would be adjoining an 8th root of unity. This would be adjoining a 4th root of unity. So here, this becomes the norm of kt over q is the norm of k2t over q applied to the norm of kt over k2t. And so now working through it, then this is the left-hand side, this is the right-hand side. Here, we note that since aq hat of 2t is an element of k2t, then the field norm, it will pull it out and will accrue the degree as the exponent. The field norm sends 1 to 1, and so we have this. This is multiplicative, so the field norm, the exponent moves outside. And this, note that k2t is the smallest number field containing aq hat of 2t, so this is just n. And then here, our computation. To do this, we note that kt over q has degree t2 over 2. By the multiplicity of field degrees, this is the degree of kt over k2t times the degree of k2t over q. We know that this is 2t2 over 2, which is t2 over 4. So we then have that kt over k2t is 2. And so this then tells us that we have this equation. And so plugging it in gives us our induction relation. So then by an induction for non-zero t, we just nest this. This is 2t, so then this is 2t squared. And we look at the pattern. Here the pattern is the power of 2 is increasing, and we can go up all the way to 2 to the negative v2 of t minus 1. Just to see where this comes from, 2 to the negative v2 of t is the denominator of t. So if we multiply by 1 power of 2 less than that, this thing is going to be equal to 1/2 in z2 hat. So this is going to be the square root of 2, and this is going to be the norm of aq hat evaluated at 1/2. But aq hat evaluated at 1/2 is the rational number 1 minus q, so that's going to be trivial. So here, note that this exponent is going to be 1 less, so our product is going to be from n equals 0 to negative v2 of t minus 2, 1 less than the exponent here, and of this thing. Now we just run through the computation. It's glorious shutting up and computing. So here, this is the p-adic absolute value of t over 2, and here this 2n becomes 1 over 2n, and likewise in the denominator. Here, the 2n exponent is going to cancel out the 2n over here, so we're left with 4 to the power of t2 over 2. We then pull this out, and we're going to accrue a factor of negative v2 of t minus 1, because that's the number of times we multiplied this quantity by itself, against itself. We then pull out another copy of 4 to the t2 over 2 from the numerator, and we put it into the denominator. This, taking the square root, it's 2 to the negative v2 of t, t2. 2 to the negative v2 of t is just t2, so this is t2 to the t2. t2 to the t2 is fun to say. Here, we're going to increase the index n by 1, which means we decrease it by 1 in the product. And then, just as a common trick, this is 2 to the negative v2 of t, so we'll pull that v2 of t to the bottom, and we get this. And now this is just a simple thing. We're going to go from n equals 1 to negative v2 of t minus 1. I'm then going to decrease n here by v2 of t, and then increase it here. The trick then is to note that v2 of t is going to be a negative number because t has a power of 2 in its denominator. So we'll now replace n with its negative, and then that flips everything around, and we get the following. Just run through it all, and we get this. And so going back to this equation, we do this, it turns into that, relabel this as n, and we get the result we want. So then this allows us to give a complete computation of the p-adic absolute value of aq hat. Let L and Q be prime numbers, with Q being odd. Then the p-adic absolute value of aq hat of t, it's going to be the following. It's the p-adic absolute value of aq hat of u2 of t times the 2-adic absolute value of L minus 1 times this product. And here t is 0. So in this case, well, this is dealing with both the familiarity and the unfamiliarity. This term right here, this thing is going to always be embeddable in QL. And so it will be expressible as a polynomial in e to the 2 pi I L minus 1's 2-adic absolute value. This quantity here is the largest 2-power root of unity contained in this field. And so because of this, we're going to use our standard embedding, our standard convention, to make sense of this, of what this absolute value is. And so to compute this L-adic absolute value, we have to use our embedding. This term, on the other hand, comes from the parts of AQ hat of t, which are algebraic over QL, and so we use the norm formula to get them. We also have the following special cases. If L is equal to 2, then the 2-adic absolute value of AQ hat of t is this thing, which the asymptotic here, as R in the reals, the 2-adic absolute value grows like the square of the denominator of t as the denominator of t goes to infinity. And if L is a prime congruent to 3 mod 4, AQ hat of t, L-adic absolute value, is going to be this. This is the unfamiliar case, and this is, in this case, the only 2-power roots of unity we can embed in QL are 1 and -1. All the other 2-power roots of unity will be algebraic over QL. So this is the simplification, and this formula reduces to this one when L is congruent to 3 mod 4. So the proof. Let T be non-zero, and for the first part, let's just suppose L is congruent to 3 mod 4. Then L minus 1 is divisible by 2, but not by 4. And so, as I said, the only 2-power roots of unity in QL are 1 and -1. This makes C2n unfamiliar to L for all n greater than or equal to 2. When L is equal to 2, on the other hand, Q2 only contains 1 and -1 as its roots of unity. Those are the only roots of unity in the field. And then C2 to the n will be unfamiliar to L for all n greater than or equal to 2. So if L is either 2 or a prime congruent to 3 mod 4, we can then use our field norm formula for the unfamiliar case to compute the L-adic absolute value. With AQ hat of t having an L-adic absolute value, it's going to be the L-adic absolute value of the field norm of AQ hat of t, and then we take the root equal to the degree of AQ hat of t over q. And this works because, again, this is a cyclotomic field, so everything's Galois. The smallest number field containing AQ hat of t is our t-tooth cyclotomic field, which has degree t2 over 2. With our lemma, we then plug this in, and so we're going to be, it's 2 over t2, and that's the exponent, and then here's the field norm, and when we do it, all this stuff cancels out. And so this is going to be the case when if L is congruent to 3 mod 4, we're done. On the other hand, if L is equal to 2, then T2 this is going to be T2 is going to be a positive power of 2. So applying the 2-adic absolute value again will give us a negative power of 2. And so we then get that this denominator is going to become big, and we're left with this thing. And now we just do a little bit of elementary number theory to deal with this quantity. Since Q is odd, there are two possibilities. Either Q is 1 mod 4 or 3 mod 4. If Q is 1 mod 4, notice that Q to the 2n plus 1 will be congruent to 2 mod 4, in which case it will be divisible by 2 exactly once, because if this was divisible by 2 twice, it would be 0 mod 4, which is not. If Q is congruent to 3 mod 4, then for any n greater than or equal to 1, this is 3 to the 2 to the n plus 1, which is 9 to the 2 to the n minus 1, this is of course 1 mod 4, and so again it's equal to 2. So for all odd primes Q to the 2n plus 1 will always be congruent to 2 mod 4 if n is greater than or equal to 1. So that means that this can never be more than a singly even number, and so it's always going to have a 2-adic absolute value of 1/2. And so this then becomes 1/2. We just do the sum. We get a nice little geometric series there. And so this is 2 to the 2 times 2 to the v2. So that's 4, and that's 1 over t2. And so that's the exact value. And if we let negative v2 of t be equal to n, that's the power, it's the exponent of 2 in the denominator of t, we get the asymptotic that this is going to be equivalent to, up to a constant, it's going to be O of 4 to the n, which is t2 squared. So all that's, and then of course, this is the 3 mod 4 case. So now let's deal with the 1 mod 4 case. In this case, we're e to the negative 2 pi I 2 to the n t is going to be a primitive t2 over 2 to the nth root of unity. Thus, as n varies from 0 to negative v2 of t minus 1 in this product, this is going to vary over a primitive 2kth root of unity, where k goes from 1 to negative v2 of t. On the other hand, ZL will contain a primitive 2kth root of unity if and only if 2k divides L minus 1. That is to say, the only way that C2k will be embeddable in ZL is if k is less than or equal to the 2-adic valuation of L minus 1. So since a q hat of t is a rational number when t is 1/2, we can just safely assume here that t2 has a 2-adic absolute value at least 4. And so what we can then do is we're going to rewrite this as follows. Here's the numerator of t, and then here's divided by 2 to the n. And is that yeah. So here I accidentally I should skip this step. I re-indexed this here. What you write this as, this would be 2 to the n times u2 of t divided by the 2-adic absolute value of t. That then becomes 2 to the n plus v2 of t times un of u2 of t, and then we do the reindexing thing where we go from positive to negative with n, and we get this. And this is useful because here this is going to be an integer, so this is a primitive 2 to the nth root of unity. As a result, this is going to be embeddable in ZL, this primitive root of unity, if and only if n is between 1 and the 2-adic valuation of L minus 1. If the negative 2-adic valuation of t is less than or equal to v2 of L minus 1, every term of this product will be embeddable in ZL, in which case we use our standard convention and Hensel liftings to compute the L-adic absolute value. So conversely, let's suppose that we have more than what we need, that negative v2 of t is bigger than v2 of L minus 1, which means that the smallest number field containing this number, it's going to contain some roots of unity which are embeddable in ZL, but it's going to contain some roots of unity which are not. And so what we're going to then do is we'll just factor it based according to the terms. Since when n equals 1, this is going to be, since this is a 2 to the nth power root of unity, if we let n go from 1 to v2 of L minus 1, this is then going to be taking the product over all of the terms that are embeddable in QL. And for here, where n is bigger than v2 of L minus 1, this is not going to be embeddable in QL. We can rewrite this by using a trick. Note that u2 of t times L minus 1's 2-adic absolute value is a fraction of the form u2 of t over 2 to the k, for some integer k equals 1. So we just evaluate a q hat of t at this number. Here, since u2 of t is an odd number, it has a valuation of 0. So, and it's because this is going to be the valuation of v2 of t plus the valuation of L minus 1. We get that. And I'm using this formula here. And the negative I got rid of because the 2-adic valuation of this thing is equal to negative times the 2-adic valuation of this thing. And then just manipulating things, we note that, let's see, where do we get it here? Yes. This is u2 of L minus 1. Since u2 kills the even part of a 2-adic integer, this is or a 2-adic rational number. This is a power of 2, so it's going to die, and so all that's left is u2 of u2, which is just u2, and so we get this, which is precisely what we had here. So this means that we can rewrite this term as that. Since the highlighted part is not embeddable in QL, the norm formula will give us its l-adic absolute value. So letting kt be this field, we then have that 1 plus that this thing's norm is equal to the norm of this, and we're going to use our formula, which gives, and because here, this is the same thing as considering 1 plus q e to the negative 2 pi I s over 4, where s is some element of z2 hat with two-adic absolute value 2 to the n. Here, this thing here is the Galois closure of the smallest Galois extension of q containing this is just a q adjoin e to the negative 2 pi I s. So this degree is equal to this degree, which is just s2 over 2. And that's 2 to the n, so that's 2 to the n minus 1. And here, since L is congruent to 1 mod 4, that means that L is an odd prime, so 4 has to have an l-adic absolute value of 1. And so, with our computation, we get this is equal to that is equal to that, and that is equal to that, which is precisely the formula we started before. And note that if L is equal to 2, or if L is equal to 3, or if L is 3 mod 4, this formula then reduces to the corresponding cases that we proved at the start. So with that, we can now we'll now let's do the bounding for the Archimedean absolute value. And so here we're going to have lower bounds and upper bounds. So the complex absolute value of this number aq hat of t, it's bounded below by t2 to the log 2 of q minus 1 over 4. And here it's t2 to its upper bound is log 2 of q plus 1 over 4. In particular, a3 hat's complex absolute value is uniformly bounded in t. The a limit as when q is greater than 5, then aq hat of t's complex absolute value tends to infinity as the denominator of t tends to infinity, and it turns out that we can then, as we'll see a little bit, we can by doing a little bit more of a more refined estimate, we can show the following lower bound, and in particular, this shows that the lim sup of a5 hat of t is going to diverge. So there are some t for which, as you go to infinity, this will be bounded, for other ones it won't be. And in particular, I'm curious if we can show that the lim inf of a3 hat of t is equal to 0. So in the proof here, blah, 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 blah. So we just note that since again, if t is non-zero, 2 to the negative v2t minus 1t is going to be congruent mod 1 to 1/2. So this is going to be negative 1. We pull out that term and we get this, and so there's a negative. Now we'll do the complex absolute value. This is just the standard, the square of the product of the conjugates. And so just working through the product, we get this thing. We rearrange it using the cosines complex representation, and we end up with the following. The trick to doing this, to estimating this, is we're going to factor out things and add and subtract, and we end up with the following. It's this quantity times this product, and here we're going to do some estimating. We note that for all theta in R, 1 minus cosine of theta is bounded between 0 and 2. So using this, we then get upper and lower estimates on this product. In particular, we get that 1 minus 4q over q plus 1, the value squared, is less than or equal to this, which is less than or equal to 1. And when we plug that in, we get this, and then we rearrange it, we get our following bounds. So note that when q is equal to 3, the lower bound here, that's going to be log base 2 of 1/2. So that's going to be negative 1. When q equals 3, the exponent of t2 in the here is going to be negative 1. And when q equals 3 here, the exponent of t2 is going to be 0, which means that which proves the boundedness of a3 hat. On the other hand, when q is equal to 5, this exponent is going to be 0, and this exponent here is going to be slightly larger than 1. That lower bound then is not going to be enough to prove divergence almost everywhere when q is equal to 5. On the other hand, when q is prime greater than or equal to 7, this exponent is going to be a positive real number, and then we get the divergence. So to improve the lower bound, we need to impose a restriction on how t2 tends to infinity. Let r be a real number strictly greater than or equal to 1/2 and strictly less than 1. I say t in z2 hat is doubling bounded if, as you multiply t by 2 to the n and then reduce the numerator of t modulo 1. So for example, if then this is bounded with the r. So as an example, suppose t was equal to 3/16. Then doubling that, we would get 6/16, which is 3/8. Doubling that, we would then get 6/8, which is 3/4, and then doubling that, we would then get 1/2. So in that case, the r that we're going to want to pick would be 3/4. That was the bound. And so here it's that this is the value of 2 to the n t mod 1, which is going to be an element of 0 to 1. So letting t be doubling bounded by r, we use the trig identity 1 minus cosine 2 pi x equals 2 times the square of sine pi x. And then we use this to rewrite this as a sine. And we note that this function is 1 periodic, so we get this. And in particular, this tells us that x then, for any x varies into reals, all that matters is the value of x modulo 1. Now, next we use a second order approximation. This is not the Taylor polynomial because the Taylor polynomial. Is it the Taylor polynomial? No, it's not the Taylor polynomial because the Taylor polynomial is an underestimate. When it is sort of second degree here, you have to go to a fourth degree to get an overestimate. And so we get this, which can just be found by fudging around with the graph. We then plug in x mod 1. And so we have sine squared of pi 2 to the nt is less than or equal to this. And since t is doubling bounded by r, this is going to be less than or equal to here, and the bound is uniform in n. So then now we just use our lower estimates. This thing, since this is a negative, this upper bound turns into a lower bound, and then we just do the arithmetic, and we end up with this fun expression. And so blah, 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 lovely computations. We have that this thing is greater than or equal to this quantity. So we take the square roots, and then this is just going to be a constant multiple. This is right here. And so then rewriting this, that's the exponent. And so what we want to show is when is this exponent going to be greater than 0? Because we need it to be greater than 0 in order to get divergence. In order for that to be true, we need for this to be greater than 0, which is the same thing as this being greater than 4. And if we raise everything to 2 and rearrange and factor it out, we get the quadratic q squared times 4, q squared plus 4 times 2r minus 1, the value squared, minus 2 times q minus 15 is greater than 0. When q equals 3, we get that either r has to be greater than 1 or less than 0, neither of which are allowed. So what this says is that this exponent will never be positive when q equals 3, because here, remember, r was defined to be between 1/2 and 1. When q equals 5, we get that either r is less than 1/2 or r is greater than 1/2. And with the quadratic here vanishing when r equals 1/2. So in this case, provided that r is greater than 1/2, so in other words, for almost all of the t, then this is going to be a positive real number when q is 5, and that proves the divergence, provided that t is doubling bounded by r. Finally, when q is greater than 5, we can rewrite this. Here, this is a positive number, and this is a positive number, so this is always going to be greater than 0, and that proves the divergence that way as well. So why is this fun? And why is it not fun? Why is this useful? Because we can do something very fun with it. And in particular, we can, so remember, the idea in my work is rather than viewing our functions as taking values in the p-adics for a fixed p. Instead, we allow our primes to vary and exploit the fact that our functions take values in global fields. AQ hat, as an example, takes values in q bar, and so we can therefore make sense of it in p-adically for any prime p. Remember that we also found that we interpreted chi-q and AQ as measures using the Parseval-Plancherel identity. And so what we're going to do is we're going to characterize the various measures we can get. So in particular, let q be an odd prime. Then let the map which sends a Schwarz-Bruhat function, so a complex valued function, this should be a 2, not a p, the complex valued locally constant function on z2, which takes f, and then we take the sum of f hat of t, aq hat of t. We denote this map by this. This is then going to be a tempered distribution in the sense that it's a continuous linear functional on the space of Schwarz-Bruhat functions, the two-adic Schwarz-Bruhat functions. And if we consider, again, this should be a 2. If we remember that W of Z2 is the Wiener algebra over Z2, which is the set of all complex valued functions on Z2 whose Fourier series representations converge absolutely. Then in this particular, we have that this recipe will give us a continuous linear functional on the two-adic Wiener algebra if and only if q equals 3. So what we're seeing here is that the divergence of AQ hat's real complex absolute value when q is greater than or equal to 5 then prevents this from being a linear functional on the Wiener algebra. So this is one way in which the q equals 3 case is completely distinct from the q greater than or equal to 5 case. This is immediately follows from the fact that that AQ hat of t's complex absolute value has power bounded growth, and so this is just a standard result for tempered distributions on locally compact abelian groups. For 2, we recall that again this is the space of all absolutely convergent Fourier series, and in particular. This as a Banach algebra, this is going to be isometrically isomorphic to the space of all absolutely summable sequences, complex valued sequences over Z2 hat, and its dual is going to be the bounded sequences. And as we saw, the AQ hat of T is bounded uniformly in T if and only if Q is equal to 3. Now here's the really fun part. We're going to consider AQ hat as the Fourier-Stieltjes transform of a 2L-adic measure for all primes L. Here we were considering it as the Fourier-Stieltjes transform of a complex valued measure or distribution. Now we're going to do all of the other completions of Q bar. So let Q and L be prime numbers with Q odd. Then this defines this recipe defines a 2L-adic measure whenever L is odd. Meanwhile, it defines a 2-adic distribution when L is equal to 2. And so here it just follows the fact that this quantity here is always going to be an L-adic. It's going to have uniformly bounded L-adic absolute value, as is this thing. And so this is just from the observation that the AQ hat for any prime L not equal to 2, it's going to be bounded in q-adic. It's going to be an L-adic integer, which means it's bounded in absolute value by 1, and therefore it defines the Fourier-Stieltjes transform of a measure. When L equals 2, our theorems, we saw that AQ hat of T grows like T2 squared, and so this then gives us a tempered distribution which acts on Schwarz-Bruhat functions. For this proof, we only really needed our fancy theorem with the field norms and everything for the L equals 2 case. For odd primes L, it suffices to note that this is an L-adic integer on top, and since L is odd, 1/4 is an L-adic integer, and so the whole thing is an L-adic integer, and we get the bound. And so, just a moral here, since the only topologies for which the resummation of the measure can converge as n approaches infinity are the q-adic topology and the real or complex topology, we observe that for any distinct odd primes q and l, our measure daq will be a 2L-adic measure whose resummation fails to converge pointwise at any z and z2. In this respect, we can say that these measures are, in a sense, more singular as 2L-adic measures when L is not equal to Q than they are as 2 q-adic measures. Here, though, the q equals 3k stands separately as its resummation is 0 everywhere, while for q greater than or equal to 5, the resummations are not identically 0. And that's the end of this episode. Our next episode, we're going to be doing frames, their full glory, and I'll also be talking about the adels. And then in episode 8, we'll let loose and just explore all the stuff that I've been working on lately. So see you then. Bye.